Welcome to Equinox, where Rob and I are striking the balance between the light and the dark. This is episode 38. My name is Joseph Darnell, and I'm joined by yours truly, the doctor in the house, Robert Carter. Hello, Rob.
Hello, Joe.
How are you doing this new week, this period post-Thanksgiving?
I'm doing well, but it feels like it's been forever since I've talked to you. It's been a week and 2 days.
It has been.
We didn't do it on Tuesday like normal. We now doing this on Thursday, and just feels like a giant gap those extra 2 days.
Yeah, for a couple of reasons. One thing was as I was recording two podcasts back to back on Mondays and Tuesdays, but also trying to crank out two other podcasts for my day job.
That's hard.
That are not on nightowl.fm, and it's all well and good. I love my shows, but I just kind of reached a point where it was like, I'm just kind of tired of the congestion between Monday, Tuesday, Wednesday.
Yeah, that makes sense.
So I asked if we could move it to Thursday. But then it also just made sense to skip Thanksgiving and Black Friday. You remember the horrors of, Friday the 13th?
Yeah.
Can you imagine? That pales in comparison to the horrors of Black Friday.
Black Friday.
Yeah. Dun, dun, dun. Did you do any shopping?
Oh, no.
Did you do any Cyber Monday?
No, I didn't. I thought about it, but I was like, nah.
Okay.
I have everything I need at the moment.
Cool. That must be so satisfying. What does it feel like to be somebody who has everything they want?
Well, it just might mean I'm broke.
We did pay attention to some sales, and we've been saving up, and we got a couch. But this kind of time period we're in, where you have to concern yourself with the shipping delays. Who knows when we're actually going to get our couch? Supposedly it's going to be here in a week, but it could be, I don't know, maybe a year from now. Who knows?
Yep. My brother-in-law has a high-end audio and home theater assembly business, basically. And he's having massive problems getting equipment.
Oh, that would be debilitating to a company.
Very rich people with very large contracts, and they're like, where's my stuff? And he's like, dude, it's just not coming from overseas. That's hard.
Ouch. Yeah. I ordered the Apple's iPhone 12 Pro a couple of weeks after it came out at the beginning of November. It arrived today.
The little one or the big one?
The middle one.
There's a middle one?
Sized, yeah.
Okay.
Yeah, there's a small, medium, and large now. And I went with the medium. It's not the most popular bestseller of the devices. The biggest one is. But I feel very happy with this device. But yeah, I ordered it a month ago and it arrived today.
Oh, I'm glad it arrived.
You didn't know that is really delayed for an Apple product like that.
Oh, okay. It's something I've been doing every Thursday now for 4 years. And that is I run a 5K in Naples, Florida with my brother-in-law and my nephew.
This time of year?
Yeah. Well, Naples is warm.
That's awesome.
It's usually too warm.
Yeah.
But it's usually like 5,000 people there. And it's just a big old fun time. And I've been I never ran since high school. And then he kind of co-opted me to go do this 4 years ago. And it was a disaster. I mean, I walked twice, it was like 36 and a half minutes. I was like, back, I used to do this in 21 minutes. I can't believe this. So then the next year was 29 and a half minutes. And then last year I was 28 minutes and 4 seconds. Oh. And this year I'm like, I'm going to do this, man. I'm breaking that. I'm going to get 27 minutes this year. Yeah, I thought. Yeah. But they didn't have it normal this year because of coronavirus. It was all a socially distanced 2 mile. So 5K is 3 miles. This is a 2 mile. And they called us up in groups and you had to wear a mask. And they stood us all 6 feet apart in 5 lanes separated by cones. And they said, go. And 5 people would run. And everyone would walk forward 6 feet. And 20 seconds later, they said, go. And 5 more people would run. So I ran 2 miles all by myself. It was the weirdest thing. I passed a couple people, and a couple people passed me. But man, I did really well. I did it in 16 minutes and 42 seconds or something like that. That's just over 8 minutes a mile, which, 52-year-old man.
Congratulations.
I mean, it's not the 5 minutes and 32 seconds I did in high school once.
Yeah.
But I can still run, man. Because a lot of people my age can't.
Congratulations.
And so I'm like, that's it. When I get home, I'm gonna run a 5K, and I'm gonna blast my last year's time. And it was 40 degrees, and I had, I was like, what do I wear? So I wore long pants and a sweatshirt and gloves, and the gloves messed up my phone. So it was right at the beginning. I was like, oh man, I my time. I should have just stopped and started again, but not. So my psych was out. And I ran it slower than last year. I was very disappointed. So today, I was like, that's it. 54 degrees today. I can go in just a long sleeve shirt and shorts, bam, let's do this. And I'm all excited. Yeah, yeah, yeah. And I did it less slower than last year again.
No.
It's the 4th kilometer.
Mm.
I mean, the first kilometer, I'm doing it in 5 minutes. I'm like, yeah. And then, I tend to slow down a little bit because I get tired. But that 4th one, I'm just like, blah. Happened twice now.
Does it make any difference if it's warmer?
Well, too warm. If it's 80 degrees or more, I can't run. It's just too hot.
Yeah. Oh, yeah.
Just as I'm getting older, I'm getting more sensitive to temperature. So some of my favorite runs are in the 30s. I just bundle up and go. Those are great.
Really?
Yeah.
I haven't done any cardio while wearing a mask. Does that seem harder? Do you feel lightheaded? Do you breathe harder?
Well, in the race, as soon as they said go, we were allowed to take off your mask.
Oh, okay.
And it was fine. I mean, literally, there was nobody around me for the whole 2 miles. And as soon as it's done, we put it back on again.
Did it seem like there was a lot of participants as usual?
I think they said there was 1,000 people.
Okay. Still pretty significant. That's nothing to sneeze at.
It was significant, but it was not crowded. They did a great job of keeping people apart. It was really weird.
Well, good.
Of course, it took me half an hour to get everyone started instead of just saying go once.
This one time I was getting together for lunch with some friends in Atlanta at a breakfast shop, a diner. And it was in a part of town that they weren't familiar with and I wasn't familiar with. And we didn't know what was going on in Atlanta. So I found the diner, but there was a Peachtree City Marathon 5K, something going on. So all the roads were roped off. There were police guidance everywhere.
This wasn't 4th of July?
It may have been, but it wasn't last year. It was maybe 2 or 3 years ago.
Okay, early summer?
Yeah. And I'd never been there when this kind of thing had happened. It's insane.
Yeah. Peachtree Road Race. There's a lot of people.
So I tried. I couldn't get a parking space. I could not find a route to the other side of the race. So I had to park on this side of the race.
Yep.
My friends made it to the restaurant because of where they were coming. And then I tried on foot to get through all the barriers. I got through one barrier after another to get to the other side. I just couldn't get to them though. So that I walked on foot through this field that was packed with the people who had already raced.
Okay.
And there were thousands of them all sweating up a storm and the air was stagnant. It was the grossest.
Good old Georgia, no wind, 100% humidity summer day.
Yeah, that's what it was. I did not get food. Instead, I got to smell Georgians.
That's funny.
It was sick.
Sorry, that's really funny.
Yeah. Well, now you had a very interesting work day. You did some new kind of article about the COVID-19. And you want to tell us about that?
Well, we're getting a lot of questions, and I'm getting them on my Biblical Genetics Facebook page, and not on MeWe now on Biblical Genetics. And we're getting people emailing us questions about the new vaccines coming out for coronavirus, and everyone's very afraid of them because of the new technology, and they're worried about genetic engineering. And a lot of people don't trust the government. A lot of people don't trust so-called big pharma. And so I said, we should write an article about this. And the boss said, yeah, we should. So I wrote a very long article. In fact, it's long enough that there's a table of contents with hyperlinks at the beginning of it. And then we sent it around to a couple of the CEOs of the company in different countries because we wanted other countries to weigh in. If they didn't like it, we could modify it. In fact, our CEO in our UK office helped a lot. He had a lot of caveats that I wasn't adding, and it made it much more robust and a lot more carefully worded. And basically, it probably bled through. I didn't say this, but I think this new vaccine technology is one of the coolest things I've ever heard, ever. I think it's brilliant. I honestly, I think it's going to be one of the safest things we've ever done. It's going to be fast. It's going to be inexpensive. And it doesn't require the use of aborted baby cells to grow.
I'm familiar with the old school approach to vaccines. What is the innovation?
The innovation is you don't use any virus at all. You don't use any bacteria or yeast at all to grow parts like they have been doing some of the more modern, like the new flu virus. They don't use the eggs anymore. From this year on, they're actually growing the stuff in either E. coli or yeast and then harvesting the protein out and using that to stick the protein in your arm. But in this case, what they do is they take messenger RNA that they make in a test tube and they take that and wrap it up in a little blob of fat, a tiny, 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 tiny little micro dot of fat. They stick that in your muscle cells in your arm, and when those little drops of fat connect to a cell, the cell will take it in. But they also take in the messenger RNA, which then will start making proteins. And as soon as your body starts making foreign proteins, your immune system goes, what is this? They see the protein, they start making antibodies, and they destroy that little cell.
Oh, interesting.
Same thing that happens in a normal viral infection. As soon as your body starts producing starts producing viruses and proteins for viruses and RNAs for viruses, your body says, and it kills the cells that are infected. That's actually how we stop an infection, by obliterating the infected cells. Cool, huh?
Oh, it's fascinating.
Yeah, but in this case, it's only a little bit of RNA. And it seems to, because they've injected this now in like 50,000 people. There's 2 big trials going on, and half of the people are getting nothing or a saline solution. Half the people are getting the real thing. But when you combine the 2 trials together, it's like 50,000 people have been given this vaccine. And it looks like it's giving us a very strong antibody response, which is great because COVID-19 doesn't necessarily give a strong antibody response, which is why some people are catching it twice. Same reason why, if a lot of people get a cold every 6 months or once a year. I hardly ever get colds, but a lot of people, they'll get colds regularly. Well, very often it's the same exact cold you got the last time or a year ago or 2 years ago. Your body just forgot.
Right.
That whole idea of lifelong immunity, that's actually an urban myth. It's not true. Immunity wanes over time. And especially with coronaviruses, they're notorious for not giving a proper immune response. So the idea of herd immunity might not ever happen if people don't generate a proper antibody response. They just might catch it again. And so this vaccine seems to be safe, and it seems to be ethical, and it seems to have a nice, good response. So I'm really looking forward to the future, because it also means that, let's say Ebola hits the world. Well, we've already have an Ebola vaccine, but say something like Ebola, which, kills 50% of the people it infects or something like that. Within a week, we can make a vaccine, literally.
Right. Wow.
And then safety testing, like this vaccine right now, the coronavirus vaccines, they had them ready in March.
Interesting.
And they've been doing safety testing ever since March.
So with the 50,000 people, they've been since March. Okay.
No. That's just since like September or October.
Oh, okay. So then other tests.
The phase 3 trials are right now. They're in phase 3 trials. And so far, everything is looking really good. And you don't need mercury. All right. Everyone's worried about mercury in vaccines. You don't need aluminum. They should be safer as long as they don't genetically engineer people, which probably is not going to happen. Another worry is that we're going to have, what's that called? Autoimmune diseases.
Oh, right.
Like lupus and things like that. They're worried that that'll trigger something in the immune system where the immune system starts attacking the body. Now, I'm not worried about this, because if that were true, it would happen a lot more often, because we get virus infections all the time. Even viruses we're immune against, when we get someone comes up with the flu that you've already had, you're not going to get the flu again, right? Oh, no, you will. Absolutely, you will. That flu virus will get into your body. It will start reproducing, but your body will kill it very quickly. And so the same thing here. If you have an immunity to the coronavirus, why would that set up a major problem when we already get these things in that natural world all the time anyway? And most people don't collapse and die from some autoimmune disease every time they get a virus. Just saying. I'm actually putting a much more positive spin on this than I did in the article. I was much more cautious in the article.
Awesome. Well, I'm glad you feel comfortable doing that.
A lot of listeners might have gotten very mad at me just now. We'll see.
Well, it's fair, and you can respond to them, but that's the best you can do. You're not trying to sway their emotions. They're responsible for being angry if that's what they are. But here I'm curious, when you say there's 2 companies or lab organizations that are doing the trials, they're using the same method. Would this mean that when the vaccine or when a vaccine becomes readily available, does that mean all the sources that supply the vaccine to countries everywhere are going to be using the same method with the same formula from virtually the same process?
Nope. There are 3 that are the furthest along, and I know a friend of mine who participated in one of the trials, and she got a 4th one. So there are at least 4 that are pretty far advanced. The one called AstraZeneca, which is the Oxford in England, Oxford AstraZeneca, they're actually using a virus to inject RNA into the cell. And that is grown on aborted fetal tissue, which has got a lot of people up in arms. And they also had some problems. They had to shut the trials down because one of the persons got very ill. And then more recently, they reported 95% effectiveness. And some people are like, wait a minute, your statistics are all messed up. So they're back to the drawing board again as far as their trials go. The other two competing ones that are the furthest along are Moderna, which is a brand new small company out of, I think, Cambridge, Massachusetts, or MIT. And the other one is Pfizer, which is a giant multinational billion-dollar company. Moderna got some money from the US government to help develop the vaccine. Pfizer did not, but they got $1 billion or so to build infrastructure so they're ready to produce 1 billion doses of the vaccine within the first year. And Singapore, I think, just approved the Moderna vaccine. And I think the UK just approved the Pfizer vaccine. I might have got them backwards.
Okay.
But this is actually good for us here in the States because that means that these trials will be happening in other countries and we'll have a large population to say, oh, wait a minute. Half the people in Singapore just died. Let's not use that vaccine. Let's use the other one.
All right.
I know it's not going to happen, but this is good. It gives us more people getting tested. And there's two competing ones that are very similar, but they're made slightly different.
Well, if you wanted to choose which version of the vaccine you took, is that possible when it is eventually publicly, officially available?
It depends on which one the U.S. government regulates or approves and how many they approve.
Okay, that makes sense.
Yeah. I mean, right now there's different flu vaccines. You got the trivalent and the quadrivalent. There's at least 2 or 3 different flu vaccines circulating now. It's always been true, but they just got rid of the egg-based one. And so in the past, there was actually probably 3 different ones, maybe 4. Now there's 2 or 3. So you just got to ask the doctor which one you're going to get. I got a lot of very positive comments and a lot of very negative comments, very few that are in between. A lot of people just thanked CMI for an even-handed approach, for being polite to the detractors, and for laying all the cards out on the table. Here's the pros and the cons, the good and the bad. And I like that approach because it helps people make a rational decision. If you only focus on the bad or you only focus on the good, you're not actually educating yourself. You're not actually making an educated and informed decision if you're only getting half the picture.
Sure.
And so that's what I tried to do. I tried to lay it all out like that, and I got a lot of comments. And then there are people who are just, the first comment I got on my Facebook thing was that red, fiery, frowny face thing, the angry face, and then all caps, I'm not going to take this. It's like, dude. One of the things I really like about our conversation here in Equinox, which, by the way, is one of the highlights of my week.
Mine too.
I'm always really looking forward to the hour I get to spend with you talking about cool stuff. But this is a kind of education that everyone needs in order to have a good rounded understanding of the way the world works and how it works. And it's not dogmatic, and we laugh our ways through the stuff we don't know, but it's also really fun to explore life. And there are so many people, and literally there are so many people, especially recently because of the rise of social media, that don't trust anything and they reject too much. They actually reject operational experimental science. And that's not where we want to go.
Let's move on to the main subject.
Yeah, I'm looking forward to this one.
You wanted to go back to the beginning, the dawn of time and the universe. Material, space, matter, the whole ball of wax.
I sure did. But also the episode where we talked about the one force that rules them all in our modern society, the law of induction. The fact that the electric field and the magnetic field are coupled.
Well, then that sounds like a great place to do a little bit of review to tie it in and segue into the universe.
All right, yeah, the cutting edge of the universe. It just so happens that there are a lot of numbers in the universe that are just numbers, like the strength of magnetic field. You know what that depends upon? Itself. It's not like you can say this plus this equals gravity, or this plus this equals electricity. These are just fundamental constants, and there's a number. There's no reason for that number existing. It just exists at that scale. It's just one of those things. You just got to take it on faith that that's the way it is. Well, scientists realized decades ago that if you tweak these just a little bit, the universe can't exist. And it's a massive problem.
What would be an example of tweaking it a little bit?
All right. Well, imagine that if you change the force of gravity just a little. Let's make the gravity just a little bit weaker. What would happen to the sun?
Well,
it would expand. There'd be less gravitational force.
See, I was thinking about all the I'm thinking about all the things orbiting the sun, and I was saying,
Oh,
well,
yeah,
if
all
it's
that too,
weaker,
all
I
that
guess we
too.
would all drift.
Yeah.
Whew. Things are starting getting cold around here.
But larger suns tend to be more red. They produce more heat and less visible light. Photosynthesis would be impossible. In fact, we'd have to be further away from the sun, and the sun would throw out more solar flares and be less stable. What happens if you increase gravitational force just a little bit? The sun would contract and become more blue. A little bit more than that, the sun becomes a black hole. We're sitting on the edge of a knife, and that's the title of the episode, The Cutting Edge of the Universe. And it's not just one knife blade. It's multiple knife blades, or if it's one knife blade, it just gets thinner and thinner and thinner. And it terrifies cosmologists because we're not supposed to be.
But why should it bother cosmologists?
Because we're not supposed to be in a special place. The universe should be easy to explain. Life should be easy to explain. We can't be special. That violates everything.
But when we look at all the other stars around us that do have planets, by the way, and
that's right,
our solar system conditions, life is not common. So if you are alive, then it's already like you've won one of the lotteries of the universe. So if you've got consciousness, it's probably here because life does exist here. Know what I'm saying? Like,
yes,
the conditions could just be right just here, and that's not a cosmic coincidence, but that's just...
Yes. There are two out clauses that scientists try to use to get away from what's called the fine-tuning argument. One is multiverse. Well, what if there's just a huge number of different universes and all the parameters in all the different universes are slightly different? Well, eventually you'll get this universe. And the other is called the anthropic principle, and I think that's what you're hinting at right now. And it's basically... If the universe wasn't like this, we wouldn't be here to discuss it.
Exactly.
The fact that we're sitting here discussing it, well, obviously it's because the universe is such that you can have carbon and hydrogen and the gravity is just right and a strong force and a weak force and the nucleus is just right and et cetera, et cetera, et cetera. And that's why we're here. So it's like a default of of course it's like that. So these are out clauses with no proof. But the philosophers, in fact, I linked a paper in the notes that's very philosophical driven, and the person is not a design advocate. So, but I really enjoyed the article, and he does a good summary of all the issues. So even though he comes to the opposite conclusion of me, I thought it was still a good review of it. If people like reading philosophy, which can be tedious sometimes, but this was actually pretty good. This is very philosophical, and it is bizarre.
I love me some philosophy.
It's bizarre that physics gets into philosophy. Why would they care? And the answer is because the physics points to a philosophical conclusion. And that is, we're not supposed to be here.
Oh, what do you mean by not supposed to be? Is there like a sign written across the universe?
Too many coincidences. when you have one coincidence, another coincidence, the probability is the probability of each times in themselves. Like, if you... I'd say if you flip a coin once, it might be heads or tails. Flip it twice, might be heads or tails. If you want two tails, that's only 1/4. It's 1/2 times 1/2. So two coincidences, you multiply them together to get the probability of both of them happening. And if you're talking about things that are like 1 out of a billion, and this other thing is 1 out of a trillion, or for both of them to be true at the same time, you multiply those things together and you get a very small number, an uncomfortably small number. And it's funny because, as a creationist, as an advocate of design, God could have created a universe that was highly probable, or he could have created a universe that was incredibly improbable. Either one is perfectly fine with me, but apparently he chose the most improbable universe that anyone could imagine. And that's what keeps a physicist awake at night. And it's funny, really funny. And this is actually a two-part argument. Most of the time, this goes to, why does life exist? But I like to broaden it out because it's not just why does life exist. It's why does the universe exist? There's a thing that Albert Einstein didn't like. He called it his biggest mistake. It's called the cosmological constant, or lambda, the Greek capital letter lambda. And basically it is something that drives the structure of the universe and has to be exactly balanced properly. If it's too strong, the whole universe collapses in upon itself. If it's too weak, the universe flies apart. And we don't see that happening because this is prior to Big Bang theory now. Big Bang didn't come up till late 50s. Einstein here is early 1900s. And he said, the universe is basically in a stable, steady state. Therefore, he balanced this thing so that everything just held together. And physicists no longer believe that. They think the universe is expanding. So you have to change lambda to do that. But if you tweak lambda just a little teeny bit, the whole universe collapses. And it's like, like the Earth and the sun, they merge together. And the whole galaxy all merges together. If you make it just a little bit the other direction, you don't even get atoms. The universe would fly apart so fast, even atoms would be ripped apart. And it doesn't take much tweaking to do this. That's the weird thing. And then even when you're just tweaking it a little bit, you can get, atoms but no stars. You can get stars that can't produce carbon. Now that's a Big Bang argument. So there's two different arguments here also. We have this idea of here's the universe as it is now. Can we explain it? And then it's, well, how do we explain the origin of the universe, which is typically a Big Bang model? I don't believe Big Bang, but fine, we can still talk about Big Bang. Don't do this right. In other words, the first generation of stars in the Big Bang model were pure hydrogen stars, and hydrogen fuses and makes helium. And then with other fusing events in second generation, third generation stars, you get things like uranium and iron and gold. But a second generation stars, you get carbon. And without that, you can't get life at all. Now, there's some other forms of life. Like what? Silicon is inappropriate. You can theoretically have some silicon compounds that are almost like biological compounds, but silicon is so limited in the number of bonds it will form compared to carbon. You take carbon, hydrogen, oxygen, and nitrogen, and you can make living things. I mean, billions of molecules. If you take silicon and add those other things, you can make a few hundred molecules maybe. So even silicon-based life isn't really practical. It's only theoretical, and it's not a very good theory. So they're really struggling. How do you get carbon? Yeah, good luck. In another way, if you change it another way, there's just too much heat. Because one of the things happens if stars burn too fast, and the rate at which stars burn is all controlled by the little subatomic forces. If they burn too fast, all you have is heat, and you don't get any stars. Cool, huh?
Yeah. So I have a theory.
Yeah?
You're saying how if gravity was a little bit heavier or a little lighter, then, these catastrophic things inevitably happen. But we're saying that the laws of the universe would be manipulated from what they are usually in the constant of our current universe. It would be sort of like how, borrowing from my background as a designer who has studied the arts and cartoons and how animators came up with their craft and how they've fed off of each other, and going back to the earliest animators from Disney up to the present, how they've all kind of like worked off of rules they made up that the audience understands, and sometimes the audience influences how animators are going to do things in the future. We all have to have certain subjective, reasons for why things are a certain way. And so there's sort of a slapstick sort of cartoon animation like the old Mickey Mouse, Donald Duck, Goofy, or Bugs Bunny, Daffy Duck, and Porky Pig, where everything that was alive seems to weigh less and be rubberized. So it's stretchy and bouncy.
Oh, we're going to talk about that actually a little later in this episode.
Okay. So everything is a little bit elastic, and everything is a little bit impervious to the elements. So the cold feels cold, but won't kill you.
Yes.
If you even freeze, you just have to thaw out. But set yourself on a fire, then you'll melt the ice cube around Daffy Duck, and then he'll be revived. If he burns, all he's got to do is jump up and down a little bit till his feet stop smoking. So there's sort of like this bizarre quality of,
yes,
well, if the laws of nature are different,
yes,
they're not just going to be different in one detail, they're going to be different in all details, so that it's conforming to its own logic.
Joe, this is brilliant. What a great analogy for discussing Planck's constant.
Great.
All right, Planck is a famous physicist, and his number, Planck's constant, is a very small number. It's 6 times 10 to the negative 34. When you get to scale smaller than that,
wow, yeah,
that's when you get into the weird physics of the subatomic world.
Yeah, okay.
At scales larger than that, you have normal matter. So remember the episode we did about quarks and how weird everything was? You're talking about things within the Planck constant, within smaller than the Planck constant. And so just everything is very strange. Well, what if you change Planck's constant? It wouldn't take too much changing, but you're trying to dribble a basketball and the basketball goes through the floor. Or you're trying to bowl and the bowling ball becomes a rolling pin of 10 bowling balls that are neither bowling ball nor are they one thing, and they kind of mush into and absorb into the bowling pins at the end of the alley.
Yeah.
That's a very cartoon world. I love that analogy. That is actually brilliant. I'm going to be using this in my discussions of Planck's constant. I might talk about it once more in my whole life, but I'm definitely going to use this.
Yeah.
So if the Planck length changes, the universe can't exist as we know it. Atoms would fuse together. Things might magically, in fact, that's funny. It's almost like the world of magic. That's what magic is. They're actually fiddling with the Planck's constant. Oh, Joe, we just explained magic.
Awesome.
Now I know why Elsa could stand in her kingdom and freeze that kingdom. I mean, the amount of heat she absorbed is equal to, like 2,000 Hiroshima atomic bombs had to channel through her little body. Well, she wasn't going through her body. She was adjusting the Planck length in the kingdom. Sorry.
That's great. I knew there had to be an explanation.
Now, before we move on to the next step, though, the cosmological constant, going back a step here, because we just jumped to the end of the notes. Let's go back to the beginning of the notes now. That has to be accurate to within 120 decimal points. So it's got to be, 1.001. And it's 120 decimal points after the decimal.
Right.
120 zeros. If you make that 002, the universe can't exist.
Oh, wow.
To 120. Now that literally, that is a knife edge that's impossibly sharp. It cannot be. It cannot physically exist. It's sharper than an atom. And that's the issue. So cosmological constant, Planck's limit, those two things we've talked about so far. Let's go to the next one now. You'll see in the notes I included a couple of diagrams.
Yes.
Those are just to stimulate conversation. And we can't say in this diagram here because no one's going to know what we're talking about. But hey, listeners, there'll be a link in the show notes for an article by Jonathan Sarfati where he reviewed a book by two physicists that discuss these things. And these diagrams are listed from there and they'll be in that article. So you just click on there and you go see what we're talking about if you want to follow us up a little bit. And I'd recommend it because it is amazingly fun. All right, Joe, I don't mean to put you on the spot.
Mm-hmm.
Do you remember from prior discussions what the 4 fundamental forces in the universe are?
Not off the top of my head.
Now, ignoring the most recently discovered one, the 5th fundamental force is duct tape. But we're going to skip over that one. All right.
Well,
I'll give you a
if
hint.
you'd caught me on a better day, I'd remember. But I am especially tired.
The strong force, the weak force, electromagnetism, and gravity.
Okay.
Those are the 4 fundamental constants in the universe. They have nothing to do with one another. You can't get from one to the other. They just are. So the strong force holds quarks together. That makes protons. Actually holds protons together to make a nucleus. So therefore, it controls alpha decay, a form of radioactive decay from the nucleus. You change that strong force a little bit, and either your nuclei are going to fuse together or fly apart.
Mm-hmm.
Change it a little bit more, you can't even get protons. How do you have atoms without protons?
That would be pretty difficult.
Oh, it'd be impossible. One of the things that weak force does, it controls gamma radiation. So change it a little bit, and all of a sudden, the universe is full of life-sterilizing gamma rays that wouldn't just come out of radioactive elements. It'd be coming out of carbon and oxygen and hydrogen, and it'd be sterilizing. There would be no life. So these things are important, very important.
Yeah. Right, of course. We appreciate all of the forces of the fundamentals.
Well, I'm glad you appreciate them. Yes. So the strong force in the nucleus, it bonds things together. If you make it a little bit weaker, you can't get deuterium, which, if you remember, is an isotope of hydrogen. It's hydrogen with a neutron. That is a precursor to forming helium inside our sun. So the fusion reaction inside the sun requires this step. Well, if you can't get that, you have no fusion. You have no stars. All the stars go dark. The electromagnetic force is what bonds the electron to the nucleus. So negative charge, positive charge, they attract each other. You change that just a little bit, and you don't get protons. You don't get nuclei. All the atoms just basically fly apart. That means you don't get stars, you don't get galaxies, you don't have an Earth, you can't have a body. The universe literally ceases to exist. It just becomes a sludge of subatomic particles. And if you take one plus the other, so the strong force has to be just as it is, and the electromagnetic force has to be just as it is, and you multiply those two things together, the universe, again, for another totally different reason, has nothing to do with the other two, totally different reason, is sitting on the edge of a knife.
Okay. This knife has many edges.
Yes. And when you start multiplying these things together, and we'll get to that in a second, I'm only going to compare three things. Okay, well, I'm talking about now. I'm going to compare it now. Remember when we talked about quarks and electrons episodes ago? And I said these are the three fundamental particles of the universe.
Yes.
From these three things, you can make everything else. But you can't break these down. So the down quark, the up quark, and the electron. If you look at how sensitive atoms are to the masses of these three things, and you start multiplying those probabilities together, and you put on a diagram, like a 3D diagram on a piece of paper, and it's okay, here's the mass of one, here's the mass of the other for the X and the Y, and the Z axis is the mass of the other. And you say, okay, here's what these have to be. And in this little region in the middle, that's where everything is perfectly balanced and we get the universe as we know it. Well, if you wanted to see that with the naked eye, you would need a piece of paper 10 light years tall. And you can see pretty small things, right?
Yeah.
But that little dot that you would see on a 10 light year tall piece of paper, that little dot is a probability of the universe existing as it exists. Now, if you change any of that, you get no universe. So this is the fine-tuning problem, and this is why physicists have gone to the multiverse theory, which cannot be disproven.
But it also doesn't seem to really answer anything. It's blind stab in the dark, right?
Yeah, why would the fundamental constants of the universe be different in different universes? Who says? And if that's true, how come all the constants in this universe are all the same? Because if it can vary from one universe to the other, why can't it vary within one universe? And if that's true, you can't know how old the universe is. You can't know how big the universe is. You can't know the speed of light. We might be living in a very odd little bubble that only encompasses our solar system, or maybe our galaxy.
I thought of a problem about the multiverse theory a while ago.
Okay.
That what if you were in a universe where one of the laws of your universe was that all universes were exactly like yours, almost like a mirror. it just breaks down.
That rule's not allowed, Joe.
Okay.
You can't. That's not one of the rules of the game here.
Yeah, breaking the multiverse rule. But you see what I mean? Like, it sounds like a really fantastic idea until there's one rule in one universe that contradicts rules of like the utmost rules of the universes.
That's funny. That's funny. So if you take a if you take a proton and you add an electron to it, you get a neutron. So a neutron is a little bit larger than a proton. It's actually a proton plus an electron plus an antineutrino, which almost has no mass. But those three things together add up to the mass of a neutron. Well, that means that matter, neutron-based, proton-based, depends on the relative masses of protons and electrons, neutrinos, things like that. You start fiddling with that, you very quickly get to a world where you only have protons. Because proton plus electron plus an antineutrino equals a neutron. You fiddle with that, you can't get neutrons, which means you can have no element other than hydrogen.
Oh, wow.
You couldn't even have any of the isotopes of hydrogen. No deuterium, no tritium. You only have hydrogen. Mess with it another way, you don't get any nuclei. Mess with it in another way, you only get neutrons. Because all the protons and all the electrons would fuse together.
Oh, wow.
And you only get neutrons, which means you have no matter. You have no elements, because the difference between one element to the other is how many protons it contains. And if all your protons are merging with all your electrons, you don't get any protons. There's no gold. There's no beryllium.
Wow.
I love this discussion. This is one of my favorites, actually. So in a Big Bang scenario, you have all the energy in the universe all of a sudden funking into existence. And then it starts spreading out. And because E equals mc squared, eventually you start getting matter, as in subatomic particles. And as it spreads out, the subatomic particles start fusing into atoms. And as it spreads out, out and out and out, you're going to get hydrogen. And those hydrogens have to form stars, which we talked about earlier, how you can't get star formation from clouds of gas. But okay, whatever. They, in their model, they start forming stars, and the stars burn, and they produce heavier elements and blow up. And those parts of those stars refuse together to make another new star, and that in turn fuses these middle elements to make all the heavier elements. How do you do that? There's so many different things that all have to be true at the same time. Or literally, that entire scenario falls apart.
It's incredible.
You have to expand at just the right rate. If you expand a little bit too fast, you don't get atoms.
Right.
A little bit too slow, and everything instantly reverses back to a big crunch. And then all these other things have to be balanced.
So what we were saying is, with the multiverse theory, there's going to be countless examples where these laws were just a little bit off.
Yeah.
So there's infinite numbers of them where everything just scattered, and then others where they just imploded into one great big clump.
Yeah.
That's the only way to make sense of it. This is one of the things about science fiction, whenever they hop from universe to universe, that always seems too convenient in and of itself, because what is to happen when your spaceship hops into a universe where all the matter drifts apart? Well, now you just killed yourself.
Or all the matter's antimatter.
Oh, yes.
I didn't mean to blow up that universe. I just blew it up.
Yes.
Do you remember, I don't know, 5-10 years ago when they discovered the God particle?
Yeah, I remember that reaching the news. I was wondering if you were going to bring that up.
Yes, because this is one of the biggest fine-tuning problems that there is. It's called the Higgs boson. This is something that was predicted years ago. And they had all these parts of all these different atoms, and it's called the basically particle theory. That all the different particles of all the subatomic parts of all the different atoms, and they said, okay, we have quarks, and we have mesons and leptons, we got neutrons and protons and electrons, and all these other things, all these combinations of things. And they said, there's something missing. There's one thing we need, and we're going to call it the Higgs boson.
Sure.
And we're going to build $1 billion, larger than Switzerland atom smasher. I don't know if it's larger than Switzerland, but it's huge. And we're going to find this thing. And they did. And it fulfilled their predictions, and everyone was very bummed. They wanted to find something weird, because any new physicist, he wants to work on a new problem. He wants to discover something no one's ever seen before. They don't want to basically confirm some 50-year-old prophecy. Well, whatever. And yet, they also wanted to run away from this. It was terrifying to them because of the fine-tuning. Now, there is a friend of mine. Her name is Mary Beth de Repentigny. Hard to say her last name, but I've tried. She knows physics. And I have seen her lecture twice, and I still don't quite understand it. And I know she's written an article that I've just refreshed. In fact, that'll be in the show notes also. It's a good article. But I don't quite understand it. This is a little bit beyond my brain. But I want to understand it.
Sure.
Because the summary from what she said is the Higgs boson has to be accurate to within 17 decimal points, or the universe can't exist.
Oh.
Now,
Wow.
It's weird enough that the things that have mass, they get their mass from the Higgs boson. Don't ask me why. I don't understand why. But it's a total mystery, a total riddle why something interacting with the Higgs has this mass, but something else has more mass or less mass. There's no reason for this. It just is. So that's weird enough. But it's not just to within 17 decimal points. It's like basically they said, okay, it's between here and here, but it's not in the middle. It's on the edge to 17 decimal points. So if it was 0.000000000000001 lighter, the universe wouldn't exist.
Oh.
It could have been on the other end. It could have been billions of fold more heavy, and they would have been perfectly happy. But it's not. It's in the most uncomfortable position that there could possibly be for a physicist. It's too perfect. So not only is the universe on the edge of a knife, it's like God stood two knives edge to edge on top of each other and balanced them.
Wow.
But these knives are sharper than atoms are sharp, and they still balance. And that is the mystery of the fine-tuning of the universe.
Sure is.
There are other fine-tuning arguments that have to do with life here on Earth. They're not like universe scale, but I mean, tons and tons and tons of them. The Earth has to be just far enough away from the sun so it's not too hot, not too cold, right? It's in the Goldilocks zone we talked about a couple episodes ago.
Yeah, as you were describing the universe conditions, it reminded me of those, the planet's conditions.
And the sun has to be just the right type of star. Not too hot, not too cold, very stable. Just the right amount of heat, just the right amount of gravity. The Earth has to have a certain mass. If it's too big, you're not going to get biological life. You can't get giraffes and elephants on Jupiter. And it can't be too small because then all the volatile atmospheric gases fly away, which is why there's no atmosphere on Mars. Gravity is not strong enough to hold in gases. And yet the gravity can't be too strong. And there can't be, one reason is that there'd be too much moisture in the air would become opaque, and then you'll get photosynthesis. Without photosynthesis, you don't get life on this Earth. And there has to be carbon, because carbon is the wonder chemical. It is the thing that allows life to exist. And there has to be water. I mean, life and water are inextricably linked together. You cannot get life without water. And it has to be liquid water. And water is one of the most bizarre substances because the frozen form is not heavier than the liquid form. And the frozen form floats, which is why you can have life under the Arctic ice cap. Lots of life because solid water floats. And it's on and on and on and on. And there's so many elements that are toxic to life. Well, they're locked away in the crust. They're not floating around freely. There's no volcanoes spewing out these things, or we would be dead.
Right.
And so there's a lot of fine-tuning parameters necessary for life. And we're looking around the universe saying, man, the universe is hostile to life. There's literally only one place in the universe we've ever been able to see where life is possible, and that's right here on planet Earth.
Not just possible, but for the most part, compared to the rest of the universe, it's pretty convenient. It's pretty good.
How so?
As a way of analogy, there's, the running meme going around that 2020 is the worst year ever. And then, what you could quip is, says the person who lives today that never had to live in another age of history. Yeah. Because, we have trying circumstances.
Yeah, Black Death.
Yeah.
Plague of Justinian, Mongol hordes.
Right. There's been some rough times of history. Just take away all the technology we have. People that lived in the first century, they never had a cup of coffee. They never had modern medicine. They never could listen to the orchestra. They never used a key to open or unlock a door. They never had automated door. They didn't have manufactured clothing. They didn't have transportation like we do. If you did, you had to clean up after your transportation. Oh,
their world wasn't clean up after your transportation. That's funny. That was one of the giant health crises, whatever, of New York City at the end of the 1800s.
Yeah.
They were literally calculating how long it would be before they're buried in horse dung.
Wow.
And it was a massive problem and getting worse as the population grew. And what are they going to do? Well, Henry Ford invented the car and saved us all from being smothered by horse poop.
So I would say that the constants are inexplicably in our favor.
Yeah.
Oh, I just realized this is like the Hunger Games. The odds are in our favor, though. Oh.
That's odd.
Well, thank you, Rob.
You're welcome.
That is a puzzling, awesome subject. Thank you, everybody, for joining us on our quest. If you want to find this episode's interesting show notes, you head over to nightowl.fm/equinox/38. If there's any way that you found this episode interesting, please consider sharing it with a friend or a family member. You should also check out Rob's Biblical Genetics, which is Rob's other exciting project. Biblical Genetics is also available on Facebook and YouTube, where you can watch the videos and join the discussions in the comments. And if you want to find me, I'm at JCS Darnell on Twitter, or take a listen to my other podcast, Hi-Fi, which is available on nightowl.fm/hi-fi. Until next time, goodbye, Rob.
Goodbye, Joe.
You have been listening to Equinox. please consider sharing it with a family, And if you would all, let me say that again, /hi-fi. I'm too tired. I'm mispronouncing everything tonight, Rob.
You're good, man. I think you came across very well tonight, actually.
Almost. Let me finish saying the word hi-fi.
Hey, you had the cartoon analogy. That was like one of the coolest things that ever happened on this show. That was brilliant.
I got 2 more sentences to say and I'll be done. Oh, made it.